Welcome to class today. I'm sure you've been following my class, and don't forget, this is Smart IQs, and this is chemistry class. Okay? The last time we met, we talked about electrolysis, intro to electrolysis, and I talked about what an electrolysis is, the chemical change, okay, that occur whenever an electric current is made to pass through an electrolyte. Okay, then I move straight to talk about what an electrolyte is. I told you that an electrolyte, of course, is a conductor in forms of aqueous solution or molten compound that allow current to pass through them and then become decomposed in that process. That is what an electrolyte is. I talked about electrode. I told you that electrode, of course, are substance that allows current to enter through them to the electrolyte and also allow current to pass through them, to leave through them, to leave the electrolyte through them. That is what an electrode is all about. Talked about anode and cathode. Of course, anode, the positive electrode through which current enters into the electrolyte, and then the cathode becomes the negative electrode through which current leaves the electrolyte. Are we together? And then we talk about electrolytic. Okay, before we talk about that, remember I remember I gave you examples of electrolyte and non-electrolyte. Okay, electrolyte, examples of non-electrolyte. I told you that copper 2 tetrasulfate 6, of course, solution aqueous is an electrolyte. Okay, among others, we have our acid solutions, alkaline solutions, electrolyte. Okay, and paraffin wax can be a non-electrolyte. Are we together? And so many other examples of which I gave you in the previous class. In case you have not been following the class, you have to go and watch the part 1 of this class. Are we together? Good. I also told you what an electrolytic cell is all about. Okay, electrolytic cell comprised of the electrolytic tank. Okay, where we have our electrolytes inside. Then we have our two electrodes, the anode and cathode, deep inside the electrolytic tank with our electrolyte connected to a battery source. That is what an electrolytic tank, a cell, is all about. Are we together? So today, without wasting much of our time, we are still going to further our electrolysis, and that is part 2. By the end of this class, you should be able to state the Faraday's laws of electrolysis. Okay, the laws propounded by Michael Faraday, you should be able to state them. Also, you should be able to solve simple calculations on electrolysis. Okay, you should also be able to state uses or application of electrolysis. Are we together? Good. So let's get down to class. Electrolysis. Of course, I told you that electrolysis is very important chemical process. Okay, electrolytic process is so important in the industrial world. Okay, so electrolysis plays a crucial role in various chemical processes and industry. Okay, and kudos to Michael Faraday, frontliners, pioneers in electrochemistry. Okay, who formulated the very two fundamental laws of that governs electrolysis. So the first one we are going to talk about. So Faraday's first law of electrolysis. The law states that the mass of substance, the mass of elements that will be deposited or discharged, okay, at the electrode will usually be directly proportional to the amount of charge that passes through the electrolyte. Okay, the amount of substance that will be liberated, that will be deposited, that will be discharged at the electrode. Okay, we have a direct relationship with the amount of charge, the quantity of electricity that passes through the electrolyte. Okay, so with that understanding, so mathematically let's express what Michael Faraday is saying. So mass of that substance that will be deposited or liberated or discharged at the electrode will always be proportional to the amount of charge. Okay, and where m is the mass of substance, and that gives us in gram. We have q, which is in coulombs, and that is electricity that passes through the electrolyte. It's known as amount of charge. Okay, so when we remove the constant of proportionality, so what are we going to get? So we have m, the mass, equals z multiplied by q. Are we together? And where our z is a proportionality constant, and that is equivalent to our electrochemical equivalent. Okay, electrochemical equivalent, and the unit is going to be gram per coulomb. Okay, gram per coulomb. Are we together? Good. So the second law that as propounded by Michael Faraday, so Faraday's second law of electrolysis states that when we have different masses, okay, of substances deposited or liberated as a result of the same quantity of electricity, okay, and that will all be proportional to their equivalent weight. What are we saying? The mass of different substances that will be discharged, okay, when we have equal quantities of electricity, this mass or these masses will be proportional to their chemical equivalent weight. Okay, so mass directly proportional to their chemical equivalent weights, where our m still represent our mass, remember, and our E represent equivalent weight of the substance. Okay, so we have a setup in a setup presented to us now, and that setup, let's pick our pen so that we can understand quickly. Good. So this setup, as we have it, so this is a substance of tetrazosulfate 6 aqueous. This is another substance of copper 2 tetrazosulfate 6 and then silver nitrate. Are we together? Good. So these are different substances but connected to what? The same source. Good. Connected to the same source. So what Michael Faraday is saying is that the masses, their masses, the mass of mass 1 and then mass 2, okay, mass 3 and mass 3, that is their mass. These masses will be proportional, okay, to their chemical equivalent, and that is why you can see whether W, okay, that represents our weight, okay, or mass, good, and where our E represents our chemical equivalent weight. Are we together? So remember the previous, we have our mass, which is equals to Z, okay, ZQ. Are we together? This is the first law, Faraday's first law. Mass is directly proportional to the quantity of what? Electricity. Very good. So, and that appears, we know that our Q, okay, quantity of electricity is equivalent or equal to current, okay, current multiplied by what? Time. Current multiplied by time. Good. So that is why you can see I told us that or Z1 IT. This IT represent our what? Our Q. Very good. Represent our Q. So, and if that is the case, this is Z and this is Q. So meaning that the whole of these represent our M. Very good. So M, okay, M1 directly proportional to chemical equivalent with 1. So the mass, okay, here will also be proportional to the chemical equivalent of this. And likewise, this also, the mass here will be proportional to chemical equivalent here, and the same thing here. Are we together? So meaning that mass 1 over mass 2, okay, will be equal to chemical equivalent weight 1 all over chemical equivalent weight 2. That is that. What is equivalent weight? That is atomic weight all over its valence. Are we together? Good. So that is our second law of electrolysis as propounded by Michael Faraday. Are we together? So let's have this problem solved before us. So the question is that how much charge is required for the following reaction? So the first one, we want to know how much charge would be required for aluminum ion, okay, who has lost 3 electrons to become an atom, okay, and then the same thing with copper 2 ions. Are we together? To become a copper atom. So solution, we know that at the electrode, okay, this is gonna be what? Reduction half equation. Are we together? So this is reduction half equation, and we have aluminum 3 ions. Aluminum, yes, charge losing 3 electrons, and when that happens, of course, this is being reduced. Okay, good. So now we are much concerned about the mode or the numbers of electrons. As far as Michael Faraday's electrolysis is concerned, or the laws, the first law, the second law, we have a constant there that tells us that 1 mole, okay, of substance will be equivalent to 1 electron. Good. And that will also be equivalent to 1 Faraday. Good. That will also be equivalent to 1 Faraday, and 1 Faraday is equal to 96,500 coulombs. Good. 96 what? 500 coulombs. Good. So you must master this. So that means when we have 2 electrons, if we have 2 electrons, okay, it means 2 electrons will be equivalent to what? 2 Faraday. Very good. Equivalent to what? 2 Faraday. Good. And that will be equal to what? That will be equal to this guy multiplied by 2. Very good. That will be multiplied by 2. So right now, I remember the question is saying we should calculate or how much charge is required for the following reaction. So how much charge will be needed, okay, for this aluminum to be reduced to aluminum atom. So that is what we are looking for, and that means I told us that the amount of charge is measured in coulombs. So indirectly we want it to be in what? In coulombs. So now checking our reduction half equation. So we have 3 electrons. So that means 3 electrons. This is equals to what? This is equals to 3F, 3 Faraday. Remember? Good. And 3 Faraday will be equal to what? 3 times what? 96,500. Good. 96,500. 3 times what? 96,500 coulombs. So whatever we have, which is equal to 289,500 coulombs. So 289,500 coulombs becomes the amount of charge for aluminum, okay, ions to be reduced to what? Aluminum atom. Are we together? So for the second equation, so without wasting much of our time, so as you can see, we have our two electrons. So if you consider what I've stated earlier, so that means 2 electrons will be equivalent to what? 2 Faradays. And 2 Faradays become 2 times 1 Faraday, which is 96,500. Then you have the amount of charge that will be needed for this to become copper atom will be 193,000 coulombs. Are we together? Good. So let's continue for more questions. So this one said, how much copper, okay, copper atom will be deposited on the cathode of an electrolytic cell containing copper 2 tetrasulfate 6 solution by the passage of a current of 2 amperes and for 30 minutes. Okay, we are given the amount of the atomic mass of copper, and that is 63.5 grams. Are we together? So how do we go about this? Remember that the electrolyte is a copper 2 tetrasulfate 6. So that means at the cathode, okay, copper 2 will be deposited or will be decomposed. Yes, very good. Copper 2 will be decomposed at the cathode. Are we together? And that means with that it's going to be reduced to copper atom, just as we have it previously. So what am I saying? We know that we have our copper 2. Okay, remember what I'm saying? Look at it. This is what will happen at the cathode, reaction at the cathode. So look at it. We have our copper 2, okay, being reduced to copper atom. Are we together? And then we have our 2 electrons. Remember what I stated earlier? 2 electrons give us what? 2 Faradays. Good. So that means 2 electrons is equivalent to what? 2 Faraday. So it takes 2 Faradays to what? Produce copper atom based on this reaction. Are we together? Now 2 Faraday, we are aware already that 2 Faraday, we calculated that in the previous slide. 2 Faraday is 193K, okay? 193 what? 193K, 193,000 coulomb. So that is 2 Faraday. So it takes 193,000 coulomb, okay, to liberate what? To liberate copper. This copper, we are going to use the atomic mass of copper, which is 63, as we have been given, 0.5. Good. 0.5. 63.5. 63 point what? 0.5. Very good. So it takes 193,000 coulombs to liberate 63.5 gram of copper. Are we together? So the question now is that what would be the amount of copper that will be deposited when a current of 2 amperes, okay, is made to pass through that solution of copper 2 tetrasulfate 6 for 30 minutes. Are we together? Now remember that. So let's skip this one. We are coming back, but remember that, let's come to this side now. Remember that we have our Q, okay, which is equals to what? I times T. Good. That is current times what? Time. Very good. Current times time. So the current is 2 amperes. The time is 30 minutes. So 2 amperes of current is made to pass through that copper 2 tetrasulfate 6 solution for 30 minutes. So we have to convert this minutes, 30 minutes to seconds. When we do that, we multiply 30 by 60, and we're going to get what? That's 1800 seconds. We have 1800 seconds. So the quantity of electricity for that particular current, and for the current and for the amount of time that current will stay inside that solution, will now become current times time. Okay, current times time, and current is 2 amperes, time is 800 seconds. So when we get that, we have our 3600 coulombs. So this is the quantity of electricity now. So what will be the amount of copper this 3600 coulombs we liberate? Are we together? Very good. So remember that we have from that our reactions at the cathode, that based on this reaction we have 193k coulombs will liberate the amount of atomic mass of copper, right? So what will 3600 liberate? Okay, what will 3600 liberate? So we don't know. So as simple as that. So what are we saying? If 193, okay, 193,000, okay, gives us 63.5 of copper, okay, 0.5 copper. So what will 3600, okay, what will 3600 provide? So as simple as ABC, cross multiply. When you do that, so you have your X. So that means for a current of 2 ampere, okay, that is made to be inside copper 2 tetraisophosphates 6 solution for about 30 minutes, it's going to give us this 63.5, then everything divided by 193,000. Very good. Are we together? Good. So when we do that, actually, so the amount of copper that will be deposited becomes 1.184 grams, and the argument can be very straightforward. What did I mean by that? If the amount of copper that will be liberated for a huge quantity of electricity of 193k, okay, is 63.5. So if you have less than 193k of charge, of course it's going to liberate lesser than 63.5 grams. Are we together? And that is why you can see that the amount of copper liberated very minute compared to 63. Are we together? Are we together? Very good. So don't forget, in case you have any question, you can always ask your question either from the comment section, or you reach out to Smart IQs and special attention will be given. Okay, I believe that you followed the class today and you've understood. You can always rewatch the video so that, or you pause and check and work. Remember to solve more examples by yourself, and that will establish your understanding. Are we okay? So application of electrolysis. Good. We talk about purification of metals such as copper. So in electrolytic process, metals such as copper, zinc are purified, okay, and this means that impure copper, as it is extracted from their ores, becomes purified by carbon smelting. Are we together? So also electrolysis help us to electroplate. So electroplating is another application of electrolysis. Okay, what is electroplating? Somebody is asking. That means is a way of coating another a metal with another substance, okay, or a substance with another substance, and we do that so that we can improve the appearance or the resistance to corrosion of that particular metal or substance that is being coated. Are we together? Good. So silver or gold plating, of course, we automatically gives an attractive appearance, okay, and this is cheaper than making the object out of the pure metals. So you can coat any metals with silver or gold, and that will improve the appearance of that particular substance. Okay, are we together? So electroplating also protects the metal that is being plated, so that in conjunction or in contact with water is going to prevent corrosion. Are we okay? Good. Galvanized steels, of course, that is still coated with zinc. Are we together? This will always prevent rusting. Okay, good. So that the zinc become more reactive. We know that rust will always lower the reactive nature of any metal. Are we together? Good. Also, application of electrolysis. Electrolysis helps in the extraction of metals. Notably, we have aluminium, magnesium, and sodium. So, electrolysis is good for the purification of metals, for electroplating, and for extraction of metals. Are we together? So you should be able to explain or give various uses of electrolysis. Are we together? So thank you for the class today. I believe you followed the class, and I'm grateful. In case you are here to subscribe, to like and share with your colleagues, you can do that, so that we have more community of smartness. Are we together? So hit the like button and subscribe. See you in the next class.